learned by playing against itself, an approach called self-play, which helped it develop and refine straight geese over time, OpenAI, 2019. Similarly, DeepMind used self-play to collect data from millions of Go games to train AlphaGo, Silver et al., 2016. Self-play is useful not just for game bots but also for general agents. You can have AIs negotiate against each other using different strategies to see which one works better. You can have one version of the model play the role of a customer with issues and another play the customer support agent. AI's paraphrasing and translation abilities can be used to augment existing datasets. For example, given the query, how to reset my password, AI can paraphrase it to create 3 new queries. 1. I forgot my password. 2. How can I change my password? 3. Steps to reset passwords. Yu et al. 2023, rewrote the 15,000 examples in math and GSM-8K in different ways to create MetaMath, a new dataset of almost 400,000 examples. They showed that their models, trained on this new dataset, outperformed larger models on related math benchmarks. It's common to use AI to translate data in high-resource languages, more available online, into low-resource languages to help train models in low-resource languages. This is useful for training a small model specializing in a low-resource language like Quechua or Lao. You can verify the quality of translations with back translation. Let's say the original English sentence is X and the translated Lao sentence is Y. You can use another model to translate the translation back into the original language, X, then compare X with the original sentence X. If they are very different, the translation Y is likely bad. AI can translate not just natural languages but also programming languages. You can use AI to translate code written in one language to another. The Llama 3 authors used code translation of their SFT dataset with a wider range of programming languages. In fact, the training of Llama 3 depends heavily on synthetic data, and the authors used many creative techniques to generate useful data. Data augmentation and synthesis, 387. For example, they used back translation to generate code explanations and documentation. Starting with code snippets, they used AI to generate explanations and documentation. They then again used AI to generate code snippets from the explanations and documentation. Only if the generated code is considered faithful to the original will the explanation and documentation be used to fine-tune the model. AI can generate data for both pre-training and post-training, though synthetic data is intentionally included much more often in post-training than in pre-training. One possible explanation for this is that pre-training's goal is to increase the model's knowledge, and while AI can synthesize existing knowledge in different formats, it's harder to synthesize new knowledge. However, as the internet becomes flooded with AI-generated content, models that rely on internet data are likely already pre-trained on synthetic data. There are also synthetic datasets such as Cosmopedia, Alal et al., 2024, a 25 billion token collection of synthetic textbooks, blog posts, stories, posts, and WikiHow articles generated by Mixtral 8x7b Instruct v0. 1. Jiang et al., 2024. Data synthesis for post-training is also more common because post-training data, including both instruction data and preference data, generally demands the most effort to produce. Using AI to pick the better response among several responses is more straightforward, much of it was already covered in Chapter 3. The main challenge is to take into account the model's biases, such as first position bias, where the model is more likely to prefer the first option. To avoid this, NVIDIA researchers asked the AI judge twice, once with the response order swapped. They picked a valid, prompt, winning, losing, triplet only when the AI judge picked the same winner both times, NVIDIA, 2024. The next section will focus on how to use AI to synthesize instruction data for supervised fine-tuning. Instruction data synthesis during instruction fine-tuning. Each example includes an instruction and a response. AI can be used to synthesize the instructions, the responses, or both. For example, you can use AI to generate instructions and humans to write responses. You can also use humans to write instructions and AI to generate responses. For instruction generation, To ensure that you generate sufficient instructions to cover your use case, you can start with a list of topics, keywords, and/or the instruction types you want in your dataset. Then, for each item on this list, generate a certain number of instructions. You can also begin with a set of templates and generate a certain number of examples per template. Note that both the topic list and templates can be generated by AI. 388 Chapter 8 Dataset Engineering. For response generation, you can generate one or more responses per instruction. For instance, to create UltraChat, Ding et al., 2023, a multi-turn dialogue dataset, the authors first asked ChatGPT to generate 30 topics about various aspects of our daily lives, such as technology, food and drink, fashion, nature, education, finance, travel, etc. For each topic, they asked ChatGPT to generate 30 to 50 subtopics. The authors then used the same model to generate instructions and corresponding responses for these subtopics. Similarly, to train Alpaca, Tauri et al., 2023, Stanford researchers began with 175 instruction, response, examples from the self-instruct seed dataset, Wang et al., 2022. These examples were originally written to cover a diverse and interesting range of uses. Alpaca authors then used a GPT-3 model, Text DaVinci 003, to generate 52,000 instruction, response, pairs that mirrored these seed examples, as shown in Figure 8.5. Figure 8.5. A seed task and a generated task used to train Alpaca. There are also many creative ways to synthesize instruction data with certain characteristics. For example, just like it's harder for humans to write longer content than shorter content, it's harder for AI to generate high-quality long responses than short instructions. The longer the response, the more chance AI has to hallucinate. What if we use human-generated responses with AI-generated instructions? Some research errors, such as Coxell et al. 2023, Li et al. 2023, and Chen et al. 2023, follow the reverse instruction approach, take existing long-form, high-quality content like STO Rise, books, and Wikipedia articles and use AI to generate prompts that would elicit such content. This yields higher quality instruction data, avoiding AI-generated hallucinations in the responses. Data augmentation and synthesis 389. 11. The implication of this is that, in theory, it's possible to train a model that can continually improve upon itself. However, whether this is possible in practice is another story. It's possible to use reverse instruction to develop increasingly powerful models without adding manually annotated data. 11. Li et al. 2023 shows how this works. 1. Start with a small number of seed examples to train a weak model. 2. Use this weak model to generate instructions for existing high-quality content to create high-quality instruction data. 3. Fine-tune the weak model with this new high-quality instruction data. 4. Repeat until desirable performance is reached. A creative approach is to use synthetic data to fine-tune a model for understanding longer contexts. For example, if your current model processes a maximum of 8K tokens but you want it to handle 128K tokens, the long context fine-tuning process might look like this: split long documents into shorter chunks, e.g., under 8K tokens. For each short chunk, generate several question-answer pairs. For each question-answer pair, use the original long document, which may exceed 8K tokens but be shorter than your target length, as the context. This trains the model to use the extended context to answer questions. The level of detail in the Llama 3 paper, Dubé et al., 2024, makes it an excellent case study for instruction data synthesis. I've already mentioned two ways in which Llama 3 synthesized data: code translation and code back translation. Both of these methods generate more data from existing code snippets. However, the authors also used AI to synthesize coding instruction data from scratch, using the following workflow. 1. Use AI to generate a large collection of programming problem descriptions that span a diverse range of topics. 2. Given a problem description and a programming language, generate a solution. Dubé et al. found that including general rules of good programming and COT reasoning helped improve response quality. 390 Chapter 8, Dataset Engineering. 12 They observed that about 20% of solutions were initially incorrect but self-corrected, indicating that the model learned from the execution feedback and improved its performance. To ensure the quality of the generated data, they employed a rigorous correctness analysis and error correction pipeline. 1. Run generated code through parsers and linters to catch syntactic errors such as missing imports and uninitialized variables. 2. Use unit tests to catch runtime execution errors. Interestingly enough, they used AI to generate these unit tests. 3. When a solution fails at any step, prompt the model to revise the code. The prompt included the original problem description, the faulty solution, and feedback from the parser, linter, and unit tests. Only examples that pass all checks are included in the final supervised fine-tuning dataset. 12 Combining all three methods together, code translation, code back translation, and code generation, Llama 3's data synthesis workflow is quite impressive. To summarize, here's how these three methods work together. 1. Use AI to generate problem descriptions. 2. Use AI to generate solutions for each problem in different programming languages. 3. Use AI to generate unit tests to test the generated code. 4. Prompt AI to fix errors in the synthesized code. 5. Use AI to translate generated code to different programming languages. Filter out translated code that doesn't pass tests. 6. Use AI to generate conversations about the code, including code explanation and adding documentation. Filter out generated explanations and documentation that doesn't pass back translation verification. Using this pipeline, Dubé et al. Were able to generate over 2.7 million synthetic coding-related examples for the supervised fine-tuning of Llama 3. 1. Data verification. Given the importance of data quality in the model's performance, it's crucial that we have a way to verify the quality of data. The quality of AI-generated data can be measured the same way you'd evaluate other AI outputs, by functional correctness and AI judges. Data augmentation and synthesis. 391. While this section focuses on synthetic data, most of the techniques can be used to evaluate the quality of training data in general. Recall the concept of evaluation-driven development from Chapter 4, where companies are more likely to create applications they can evaluate. Similarly, people tend to synthesize data they can verify. Coding is one of the most popular foundation model use cases because it can be functionally evaluated, and for the same reason, coding-related examples are among the most commonly synthesized data. Most of the synthetic data used to train Llama 3 is coding-related. All three methods the authors use to synthesize data result in data that can be programmatically verified, by code execution and back translation. For synthetic data that can't be verified by functional correctness, it's common to use AI verifiers. An AI verifier can be a general-purpose AI judge or a specialized scorer. There are many ways to frame the verification problem. In the simplest form, the AI verifier can assign each generated example a score from 1 to 5 or classify each exam PLE as good or bad. You can also describe to a foundation model the quality requirements and instruct the model to determine if a data example meets these requirements. If you care about the factual consistency of data, you can use the factual inconsistency detection techniques discussed in Chapter 4 to filter out examples that are likely to contain hallucinations. Depending on the use case and the generated data, you can also get creative. For instance, if you want synthetic data to mimic real data, its quality can be measured by how difficult it is to distinguish between the two. You could train an AI content detector to identify AI-generated data. If it's easy to differentiate between real and synthetic data, the synthetic data isn't good. Or, if you want the synthetic data to resemble high-quality academic work, you could train a classifier to predict whether a generated paper would be accepted at a prestigious conference like NeurIPS, the Conference and Workshop on Neural Information Processing Systems, and discard any papers predicted to be clear rejects. You can have a model to detect the topic of each generated example and then remove examples whose topics are irrelevant to your task. If you expect all data to follow a similar pattern, you can also use anomaly detection to identify outliers. Outlier examples might be of low quality. Just like real data, synthetic data can also be filtered using heuristics. In general, you might want to remove examples that are empty or too short for your application. If an example is too long, you might want to truncate or remove it. You can filter out data by keywords, by user/author, by creation date, by metadata, or by source. For example, the self-instruct authors, Wang et al. 2022, filtered out generated examples using the following heuristics. 392, Chapter 8, Dataset Engineering. 13. The same issue can happen with human annotations. If the human labeler uses the knowledge they have but the model doesn't to answer a question, they are effectively teaching the model to hallucinate. Repetitive examples instructions that are too long or too short examples with the same instruction but different responses examples where the output is a repetition of the input. Even though there are many techniques to evaluate synthetic data, evaluation remains challenging. As with other AI applications, the ultimate quality test for AI-generated data is its real-world performance, whether it can improve the model's performance, and synthetic data has passed this test for many models. Limitations to AI-generated data. Given the increasing usefulness of synthetic data, it's exciting to imagine the possible ity of never having to worry about human annotated data again. However, while the role of synthetic data will certainly continue to grow in importance over time, AI-generated data might never entirely replace human-generated data. There are many reasons why, but the four major ones are the difference in quality, the limitations of imitation, potential model collapse, and the way AI generation of data obscures its lineage. Quality control. AI's generated data can be of low quality, and, as people never tire of saying, garbage in, garbage out. As mentioned earlier, people will be hesitant to use synthetic data if they can't verify its quality. Being able to develop reliable methods and metrics to evaluate data will be essential in making synthetic data more useful. Superficial imitation. As warned by the false promise of imitating proprietary LLMs, Goodaband et al., 2023, the perceived performance achieved by mimicking might be superficial. This research shows that the imitation models are good at mimicking the style of the teacher models but might struggle with factual accuracy and generalization to tasks outside the training data. Worse, imitation can force the student model to hallucinate. Imagine if the teacher model is capable of answering complex math questions, so its responses to those questions are solutions. Training a student model on these solutions effectively teaches it to produce answers that look like solutions, even if the student model isn't capable of solving these questions. 13. Goodaband et al. 2023 suggest that for improvement in reasoning capabilities, we need to focus on improving the quality of the base models. Data augmentation and synthesis. 393. 14. The concept was also later explained by the same authors in AI Models Collapse when trained on recursively generated data. Nature, July 2024. Potential model collapse. It's also unclear how much AI-generated data a model can train on. Some studies have shown that recursively using AI-generated data in train-ing causes irreversible defects in the resulting models, degrading their performance over time. In recursive recursion, training on generated data makes models forget. Shumilov et al. 2023 named this phenomenon model collapse and demonstrate its occurrences in models including variational autoencoders, Gaussian mixed-Tor models, and LLMs. Model collapse can happen during both pre-training and post-training. 14. One possible explanation is that AI models are more likely to generate probable events, e.g., not having cancer, and less likely to generate improbable events, e.g., having cancer. Over multiple iterations, probable events become overrepresented, whereas improbable events become underrepresented in the generated data. This causes models to output more common events over time while forgetting rare events. Is model collapse inevitable? Gerstgrasser et al. 2024 argue that while model collapse is inevitable if the entire training dataset is synthetic, it can be avoided by mixing synthetic data with real data. Bertrand et al. 2023, and Domitov et al. 2024, show similar results. However, none of these papers has a definitive recommendation for the proportion of synthetic data to real data. Some people have been able to improve model performance using a large amount of synthetic data. For example, common 7B language models already possess strong math capabilities, Lee et al. 2024 demonstrates that synthetic data is nearly as effective as real data in fine-tuning Llama 2-7B models on math problems. In their experiments, synthetic data shows no clear saturation when scaled up to approximately 1 million samples. Similarly, Nematron 4340B Instruct, NVIDIA, 2024, used 98% synthetic data during its instruction fine-tuning and preference fine-tuning phase. However, these experiments were carried out for only one model iteration. AI-generated data might also perpetuate biases. Data feedback loops, model-driven amplification of dataset biases, Tauri and Hashimoto, 2023, demonstrates that when models are trained on datasets that include previous model outputs, any existing biases in the model can be amplified. The authors find that the more faithful the model's outputs to the characteristics of the original training distribution, the more stable the feedback loop, thus minimizing the risk of bias amplification. 394, Chapter 8, Dataset Engineering. Obscure data lineage. This limitation of AI-generated data is more subtle. AI-generation obscures data lineage. AI models are influenced by their training data and can sometimes regurgitate it without the user knowing. This creates risks. Let's say you use Model X to generate data to train your model. If Model X was trained on data with copyright violations, your model might also violate copyrights. Or imagine you then use benchmark B to evaluate your model, which shows a strong performance. However, if Model X was also trained on benchmark B, your result on B is contaminated. Without clear data lineage, it's hard to assess a model's commercial viability or trust its performance. We've discussed how to use AI to generate data and how to evaluate the generated data, as well as its limitations. In the next section, let's switch gears to discuss one special use case of data synthesis where AI-generated data isn't just supplementary but is required: model distillation. Model distillation, also called knowledge distillation, is a method in which a small model, student, is trained to mimic a larger model, teacher, Hinton et al., 2015. The knowledge of the big model is distilled into the small model, hence the term distillation. Traditionally, the goal of model distillation is to produce smaller models for deployment. Deploying a big model can be resource-intensive. Distillation can produce a smaller, faster student model that retains performance comparable to the teacher. For example, DistillBERT, a model distilled from BERT, reduces the size of a BERT model by 40% while retaining 97% of its language comprehension capabilities and being 60% faster, San et al., 2019. The student model can be trained from scratch like DistillBERT or fine-tuned from a pre-trained model like Alpaca. In 2023, Tauri et al. Fine-tuned Llama 7B, the 7 billion parameter version of Llama, on examples generated by Text DaVinci 003, a 175 billion parameter model. The resulting model, Alpaca, behaves similarly to Text DaVinci 003, while being 4% the size of the teacher model. Not all models can be distilled. Many model licenses prohibit using their outputs to train other models, particularly to train competing models. Data augmentation and synthesis 395. 15. Comparing the parameter count of a mixture of experts model like Mixtral to that of a dense model like Nematron 4 isn't fair, but the point that the teacher model, Mixtral, is smaller than the student model, Nematron 4, still holds. Synthetic instruction data is commonly used together with adapter-based techniques, such as LoRa. For example, BuzzFeed fine-tuned a FLAN T5 model using LoRa and examples generated by OpenAI's Text DaVinci 003. The resulting model reduced their inference cost by 80%, though it was unclear how well the model performed, 2023. Note that not all training with synthetic data is model distillation. Model distillation implies that the teacher model's performance is the student's gold standard. However, it's possible to use synthetic data to train a student model that is larger and more powerful than the teacher. Model bootstrapping with reverse instruction, Lee et al., 2023, discussed in the previous section, is one example. Another example is NVIDIA's Nematron 4. A team of NVIDIA researchers first pre-trained a 340B parameter base model. This base model was then fine-tuned using instruction and preference data generated by Mixtral 8x7b Instruct v0. 1. Jiang et al., 2024, a 56 billion parameter mixture of experts model. 15. The resulting student model, Nematron 4-340b Instruct, outperformed the teacher model on a variety of tasks, NVIDIA, 2024. The Llama 3 paper notes that while training on data generated by a more competent model can significantly improve a model's performance, training indiscriminately on self-generated data doesn't improve the model's performance and can even degrade it. However, by introducing mechanisms to verify the quality of synthetic data and using only verified synthetic data, they were able to continually improve a model using its generated data. Data processing data needs to be processed according to the requirements of each use case. This SEC tie-in discusses some data processing steps for reference. I find it helpful to read model papers that disclose their dataset details, as they often contain great tips on how the researchers curated, generated, and processed data. 396, Chapter 8, Dataset Engineering. With a large amount of data, each of these processing steps can take hours, if not days. Tips to help optimize efficiency during the process include: you can do these data processing steps in whichever order saves time and compute. For example, if it takes more time to clean each example than to deduplicate data, you might want to remove the duplicated examples first before cleaning them. But if deduplication takes more time than filtering out low-quality data, filter out low-quality data first. Always do trial runs to validate that your processing scripts work as expected before applying the scripts to all your data. Avoid changing data in place. Consider keeping a copy of the original data for two reasons: you or another team might need to process the data in different ways for other applications. Bugs in your scripts can potentially corrupt your data. Inspect data. Let's say that after combing through public and internal data, you've gathered a raw dataset. The first thing to do is inspect the data to get a sense of its quality. Get the data's information and statistics. Where does the data come from? How has it been processed? What else has it been used for? Plot the distribution of tokens, to see what tokens are common, input lengths, response lengths, etc. Does the data use any special tokens? Can you get a distribution of the topics and languages in the data? How relevant are these topics and long gauges to your task? You can be creative in the statistics to use to understand your data. For example, a group of Microsoft researchers, 2023, used the distribution of verb, direct object, noun, pairs and response length to compare the difference between GPT-3's and GPT-4's generations for the same set of instructions, as shown in Figure 8.6 and Figure 8.7. This type of analysis is helpful not only to evaluate data but also to evaluate models. Data processing, 397. Figure 8.6. One statistic you can use is the distribution of verb, direct object noun, in your data. Image from Instruction Tuning with GPT-4, Peng et al., 2023. Figure 8.7. The distribution of response length for GPT-4 and GPT-3. Image from Instruction Tuning with GPT-4, Peng et al., 2023. GPT-4 seems to have a broader and more diverse range of verb-noun pairings and tends to generate longer responses. Plot these distributions by data source, time, annotator, etc. Do you notice any case tie-in patterns that tend to get longer/shorter responses or higher/lower scores? Are there any outliers? What might be the cause of these outliers? What to do with them? If the scores are supposed to follow a normal distribution, do scores by all annotators follow a normal distribution? You might notice that some annotators tend to give much shorter responses or bias toward higher scores, and it's up to you to decide what to do with their annotations. If each example has more than one annotation, compute the interannotator disagreement. Check the examples with conflicting annotations and resolve the conflicts. 398 Chapter 8 Dataset Engineering. There are many data exploration tools you should use, but they won't be replacements for manual data inspection. In every project I've worked on, staring at data for just 15 minutes usually gives me some insight that could save me hours of headaches. Greg Brockman, an OpenAI co-founder, tweeted, "Manual inspection of data has probably the highest value to prestige ratio of any activity in machine learning. Look at your data to see if the examples make sense. If it's annotated data, pick out a few queries and try to annotate them yourself to see if your annotations match the given annotations. This will give you a sense of how trustworthy the annotations are. Fact-check the responses. How unique are the examples? Are there any examples with the same query but with different responses? Are there any examples with the same responses but with different queries? Deduplicate data. Duplicated data can skew the data distribution and introduce biases into your model. Imagine a dataset that looks like Table 8.3. The duplicated entries might lead the model to the wrong conclusion that all red-colored items should be expensive. Duplications can cause test set contamination. When splitting duplicated data into train and test sets, one example might be in the train set and its duplicate in the test set. Table 8.3. A toy dataset with duplicate examples in gray cells. Input, product description, output, price, 1, item, pencil, color, red, $20 2, item, compass, color, green, $2 3, item, pencil, color, red, $20 4, item, pencil, color, red, $20 5, item, pencil, color, green, $1. Multiple studies have shown the negative impact of training data duplications on model performance. See Lee et al. 2021, and Tirumala et al. 2023, an Anthropic study demonstrated that repeating 0.1% of the data 100 times can cause an 800M parameter model's performance to degrade to that of a 400M parameter model despite the other 90% of the training tokens remaining unique. Hernandez et al., 2022. Even when duplications don't hurt your model's performance, they can waste your time and compute. Depending on the data, there are many forms of duplication, some of which are harder to detect. For example, here are a few types of duplications in a dataset of documents. Data processing, 399. 16. One of my open-source libraries, LazyNLP, also supports overlap estimation and deduplication using Bloom filter. Whole document duplications, the same document appearing more than once. Interdocument duplications, e.g., the same paragraph appears twice in one document. Cross-document duplications, e.g., the same popular quote appears in multiple documents. What can be considered duplications also depends on your definition. For example, do you want to deal with duplications at the document level, paragraph level, sentence level, or token level? Would two texts have to match exactly to be considered duplicates, or would an 80% overlap be sufficient? Are two lists considered duplicates if they have the same items but in different order? The task of deduplication can leverage the same techniques used for similarity measurements, discussed in Chapter 3. Data deduplication is also used for identity resolution, determining whether two identities, e.g., two social media profiles, are the same. Here are some concrete ways you can deduplicate data. Pairwise comparison. Compute the similarity score of each example to every other example in the data set, using exact match, n-gram match, fuzzy match, or semantic similarity score, as discussed in Chapter 3. This approach can be expensive with large datasets, however. Hashing hash examples into different buckets and check only among examples that fall into the same bucket. Hash-related deduplication methods include minhash and Bloom filter. Dimensionality reduction. Use a dimensionality reduction technique to first reduce the dimensions of your data and then do a pairwise comparison. Many techniques used for vector search, as discussed in Chapter 6, can be used for this. A quick search will return many libraries that help with deduplication. Some of them are Dupe Guru, Dedupe, DataSketch, Text Distance, The Fuzz, and Deduplicate text datasets. 16400 Chapter 8, Dataset Engineering. Clean and filter data. Data needs to be clean to make your model performant and safe. First, you might want to remove extraneous formatting tokens. Since many public datasets are scraped from the internet, extraneous HTML tags are quite common. Unless you want to train your model on HTML tags, remove them. Databricks found that removing extraneous Markdown and HTML tokens improved their model's accuracy by 20% while reducing their input token lengths by 60%. You need to clean your data of anything that isn't compliant with your policies, such as PII, sensitive data, copyrighted data, or data that is considered toxic. Techniques discussed in Chapter 4 can help. Remove all the fields that you're not allowed to use, such as zip code, name, and gender. You also might want to remove low-quality data, using techniques discussed in Data Verification on page 391 to detect low-quality data. Manual inspection of data is especially important in this step. Staring at data might help you notice patterns that you can use as heuristics to detect low-quality data. Heuristics to detect low-quality data might be non-obvious. For example, Kern et al. 2024 found that annotations made in the second half of an annotation session are of lower quality, likely due to annotator boredom or fatigue. If there is more data than you need or can afford to use, e.g., due to your compute budget, you can further filter your data. For example, you can use active learning techniques to select examples that are the most helpful for your model to learn from. You can also use importance sampling to find examples that are most important to your task. Their efficiencies depend on whether you have a good way to evaluate the importance of each training example. Meta-researchers, in their paper on data pruning, Sorcher et al., 2022, concluded that the discovery of good data pruning metrics can significantly reduce the resource costs of modern deep learning. Format data. Once you've deduplicated and cleaned your data, you need to get it into the right format expected by the model you're fine-tuning. Each model uses a specific tokenizer and expects data in a specific chat template, as discussed in Chapter 5. Getting data into the wrong chat template can cause strange bugs in your model. If you're doing supervised fine-tuning, your data is most likely in the format instruct tie-in response. Instructions can be further decomposed into system prompt, user prompt. If you've graduated to fine-tuning from prompt engineering, the instructions used for fine-tuning might be different from the instructions used during prompt engineering. During fine-tuning, instructions typically don't need task data processing. 401. Descriptions or examples. If you have sufficient training examples, the model can learn the expected behavior of the task from the examples directly. As an example, imagine that you've been using this 3-shot instruction for your food classification task with a base model. Label the following item as either edible or inedible. Item, burger label, edible item, car label, inedible item, mushroom label, edible item, input, label. For fine-tuning, all the examples included in the 3-shot prompt can be converted into training examples. The training data for fine-tuning will look like Table 8.4. Table 8.4. Example training data used for a food classification task. Example ID input-output 1 burger edible 2 car inedible 3 mushroom edible. Once the model is fine-tuned, you can use a prompt as simple as input. This is much shorter than the prompt used with the base model. Therefore, if you're worried about the input tokens of your instructions, fine-tuning can be one way to help manage the cost. Different fine-tuning data formats can impact your fine-tuned model's performance. Experiments to determine the best format for you can be helpful. When you use the fine-tuned model, make sure that the prompts you use match the format of the fine-tuning data. For example, if the training data uses the prompt in the format burger, any of the following prompts can cause issues. 402, Chapter 8, Dataset Engineering. Burger, missing the end arrow item, burger, extra prefix burger, extra space appended summary. Even though the actual process of creating training data is incredibly intricate, the principles of creating a dataset are surprisingly straightforward. To build a dataset to train a model, you start by thinking through the behaviors you want your model to learn and then design a dataset to show these behaviors. Due to the importance of data, teams are introducing dedicated data roles responsible for acquiring appropriate datasets while ensuring privacy and compliance. What data you need depends not only on your use case but also on the training phase. Pre-training requires different data from instruction fine-tuning and preferred fine-tuning. However, dataset design across training phases shares the same three core criteria: quality, coverage, and quantity. While how much data a model is trained on grabs headlines, having high-quality data with sufficient coverage is just as important. A small amount of high-quality data can outperform a large amount of noisy data. Similarly, many teams have found that increasing the diversity of their datasets is key to improving their model's performance. Due to the challenge of acquiring high-quality data, many teams have turned to synthetic data. While generating data programmatically has long been a goal, it wasn't until AI could create realistic, complex data that synthetic data became a practical solution for many more use cases. This chapter discussed different techniques for data synthesis with a deep dive into synthesizing instruction data for fine-tuning. Just like real data, synthetic data must be evaluated to ensure its quality before being used to train models. Evaluating AI-generated data is just as tricky as evaluating other AI outputs, and people are more likely to use generated data that they can really evaluate. Data is challenging because many steps in dataset creation aren't easily automatable. It's hard to annotate data, but it's even harder to create annotation guidelines. It's hard to automate data generation, but it's even harder to automate verifying it. While data synthesis helps generate more data, you can't automate thinking through what data you want. You can't easily automate annotation guidelines. You can't automate paying attention to details. However, challenging problems lead to creative solutions. One thing that stood out to me when doing research for this chapter is how much creativity is involved in dataset summary. 403. Design. There are so many ways people construct and evaluate data. I hope that the range of data synthesis and verification techniques discussed in this chapter will give you inspiration for how to design your dataset. Let's say that you've curated a wonderful dataset that allows you to train an amazing model. How should you serve this model? The next chapter will discuss how to optimize inference for latency and cost. 404 Chapter 8 Dataset Engineering. Chapter 9 Inference Optimization. New models come and go, but one thing will always remain relevant: making them better, cheaper, and faster. Up until now, the book has discussed various techniques for making models better. This chapter focuses on making them faster and cheaper. No matter how good your model is, if it's too slow, your users might lose patience, or worse, its predictions might become useless. Imagine a next-day stock price prediction model that takes 2 days to compute each outcome. If your model is too expensive, its return on investment won't be worth it. Inference optimization can be done at the model, hardware, and service levels. At the model level, you can reduce a trained model size or develop more efficient architectures, such as one without the computation bottlenecks in the attention mechanism often used in transformer models. At the hardware level, you can design more powerful hardware. The inference service runs the model on the given hardware to accommodate user requests. It can incorporate techniques that optimize models for specific hardware. It also needs to consider usage and traffic patterns to efficiently allocate resources to reduce latency and cost. Because of this, inference optimization is an interdisciplinary field that often sees collaboration among model researchers, application developers, system engineers, compiler designers, hardware architects, and even data center operators. This chapter discusses bottlenecks for AI inference and techniques to overcome them. It'll focus mostly on optimization at the model and service levels, with an overview of AI accelerators. One is discussed in Chapter 7, inference involves the forward pass while training involves both the forward and backward passes. A friend, Mark Sarufim, pointed me to an interesting relationship between a model's training cost and inference cost. Imagine you're a model provider. Let T be the total training cost, P be the cost you're charging per inference, and N be the number of inference calls you can sell. Developing a model only makes sense if the money you can recover from inference for a model is more than its training cost, i.e., T equals P times N. The more a model is used in production, the more model providers can reduce inference cost. However, this doesn't apply for third-party API providers who sell inference calls on top of open-source models. This chapter also covers performance metrics and trade-offs. Sometimes, a technique that speeds up a model can also reduce its cost. For example, reducing a model's pre-scission makes it smaller and faster. But often, optimization requires trade-offs. For example, the best hardware might make your model run faster but at a higher cost. Given the growing availability of open-source models, more teams are building their own inference services. However, even if you don't implement these inference optimization techniques, understanding these techniques will help you evaluate inference services and frameworks. If your application's latency and cost are hurting you, read on. This chapter might help you diagnose the causes and potential solutions. Understanding inference optimization. There are two distinct phases in an AI model's lifecycle: training and inference. Training refers to the process of building a model. Inference refers to the process of using a model to compute an output for a given input. Unless you train or fine-tune a model, you'll mostly need to care about inference. This section starts with an overview of inference that introduces a shared vocabulary to discuss the rest of the chapter. If you're already familiar with these concepts, feel free to skip to the section of interest. Inference overview. In production, the component that runs model inference is called an inference server. It hosts the available models and has access to the necessary hardware. Based on requests from applications, e.g., user prompts, it allocates resources to execute the appropriate models and returns the responses to users. An inference server is part of a broader inference service, which is also responsible for receiving, routing, and possibly pre-processing requests before they reach the inference server. A visualization of a simple inference service is shown in Figure 9.1. 406, Chapter 9, Inference Optimization. Figure 9.1. A simple inference service. Model APIs like those provided by OpenAI and Google are inference services. If you use one of these services, you won't be implementing most of the techniques discussed in this chapter. However, if you host a model yourself, you'll be responsible for building, optimizing, and maintaining its inference service. Computational bottlenecks. Optimization is about identifying bottlenecks and addressing them. For example, to optimize traffic, city planners might identify congestion points and take measures to alleviate congestion. Similarly, an inference server should be designed to address the computational bottlenecks of the inference workloads it serves. There are two main computational bottlenecks: compute-bound and memory bandwidth-bound. Compute-bound. This refers to tasks whose time to complete is determined by the computation needed for the tasks. For example, password decryption is typically compute-bound due to the intensive mathematical calculations required to break encryption algorithms. Memory bandwidth-bound. These tasks are constrained by the data transfer rate within the system, such as the speed of data movement between memory and processors. For example, if you store your data in the CPU memory and train a model on GPUs, you have to move data from the CPU to the GPU, which can take a long time. This can be understanding inference optimization. 407. 3. Anecdotally, I find that people coming from a system background, e.g., optimization engineers and GPU engineers, use memory-bound to refer to bandwidth-bound, and people coming from an AI background, e.g., ML and AI engineers, use to memory-bound to refer to memory capacity-bound. For the Roofline paper uses the term memory-bound to refer to memory bandwidth-bound, shortened as bandwidth-bound. In literature, memory bandwidth-bound is often referred to as memory-bound. Terminology ambiguity: memory-bound versus bandwidth-bound. Memory-bound is also used by some people to refer to tasks whose time to complete is constrained by memory capacity instead of memory bandwidth. This occurs when your hardware doesn't have sufficient memory to handle the task. For example, if your machine doesn't have enough memory to store the entire internet. This memory is often manifested in the error recognizable by engineers everywhere: OOM, out of memory. 3. However, this situation can often be mitigated by splitting your task into smaller pieces. For example, if you're constrained by GPU memory and cannot fit an entire model into the GPU, you can split the model across GPU memory and CPU memory. This splitting will slow down your computation because of the time it takes to transfer data between the CPU and GPU.